Hello.
Hello.
Good afternoon. We have just few things. Let me zoom in. There's homework 8. That's due Monday. Midterm 3. That's 2 weeks from today. The quiz was pretty much answered in the lecture last time. It asked about what are the conservative forces you have come across. At least if you go by the course, conservative forces are, one is the gravitational gravity. Any force that we have written a potential energy associated with that, that's a conservative force. U is equal to mgh here. So I should say this is uniform gravity. Second is the force due to the spring, where U is equal to half kx squared. Even though we have seen forces like normal force, force due to friction, force due to the tension, those forces are not conservative. We don't associate a potential energy to them. Today, I want to extend whatever we talked about last time a little bit, that this is broadly called stability analysis. So let me, before I talk about stability analysis, let me say something about maxima, minima in calculus. So this is maxima and calculus. Should have come across this somewhere in a math course, but a small summary is if you have a function y is equal to, let's say, f of x, and it could look like the following. So this is x, and if I were to plot this function y, I could have a function like this. That's an arbitrary function I drew. And I would like to know, let me also change this a little bit. This might grow there. And we could ask the question, what are the points at which the function is an extrema or local maxima or minima. So we're talking about local maxima or maximum or minimum, let's say. That means to say, if I were to ask when is this function a maximum, then you would say, oh, that's somewhere here. Right? But that's not the point we're interested in, locally maximum or minimum. That means to say, pick any point and move it a little bit. Is the tendency of the function to stay the same, or does it increase or decrease? Like, for example, this point here, if I were to go on the left side, right side of the axis, the function increases. On the left side of the x-axis, it decreases. So that's not okay. But this is a very good example. If I go to the right, it increases. Go to the left, it also increases. That means there is a point here which is less than any other point in the closest neighborhood. Do the same analysis here. If I go a little bit to the right, it is lower than the value here. Go a little bit to the left, it is lower. So there exists a point somewhere there which is greater than every other point on the or in its neighborhood. That's the idea. And it's clear that whenever you have those kind of points, there is one here, and one here. This point doesn't count on that because there is no neighborhood to the left-hand side to begin with. And even otherwise, this is just a minima or a maximum, but that's not what we are interested in. This is the 3 points we are interested in. And at all these 3 points, clearly, the slope of the function is equal to 0. Slope is the angle that the tangent to that point makes with respect to the x-axis, and it's very clearly 0. So if we were to find that, the first derivative of the function, let's have a specific example. Since we're going to, let's change this function so that I can be very concrete. So let's say, let me say the example is x minus x cubed. There are no units associated with this. These are all dimensionless quantities. So this is a mathematical function. So x is dimensionless here. And x minus x cubed, we have come across this before. And this looks like this. And if I were to ask when does this function go to 0, it seems like there are 3 points it goes to 0. How do I find them? X minus x cubed has to be equal to 0. So x times 1, 1 minus x cubed, x squared has to be equal to 0. That means either x is equal to 0 or x has to be equal to plus or minus 1. Right? So there are 3 solutions in there. So that's your plus 1. That's your minus 1, and that's your 0. That's the 3 points where it goes to 0. But we are interested in these points, right, where the slope is actually 0. That will be those points there. How do I find that? Take the derivative. Derivative of this function is 1 minus 3x squared. And then I have to set that equal to 0. I set this equal to 0. I get x is equal to plus or minus 1 over root 3. And that's equal to, you get the actual numbers there. Is it 1 divided by? That's about 0.58 or 0.6, let's say it's 1 sig digit. So that's 0.6, and that's here. This is 0.6, and plus or minus, right? And that's minus 0.6. That's good. So we have used these concepts before in this course. Now, what is going to be new is that now we would like to know what's the difference between these 2 points. Clearly, one is having a maximum value and the other is having a minimum value. Can we really distinguish algebraically? Geometrically, of course, it is very clear once you plot it, it's obvious that there is a maxima here and a minima here. But how does this, how can we find this out using the idea of calculus or algebraically? So what you'll do is we'll take the second derivative. So second derivative has this idea of whether it is a maxima or a minimum. So second derivative of this function, before I set this equal to 0, is equal to minus 6x. So how does that tell me whether it is a maximum or a minimum? So what I do is I evaluate. So there are 2 points, plus or minus 0.6. I would like to check what is it? Is it a maxima or a minima? So I take the second derivative, which is actually minus 6x, but then I evaluate that at x equal to, let me say, plus which is the same as, I do minus 6x. I evaluate it at x equal to 0.6. So x equal to 0.6, that makes it 3.6, right? So that's minus 3.6. Since it is negative, we are going to conclude that this is a maximum point. So the idea is that take the second derivative, and if that value comes out to be less than 0, that implies that's a maximum, or a local maximum. So we have learned by taking the second derivative and showing that it is less than 0, that the function at x equal to 0.6 has a maximum point. If that is the case, what happens when x is equal to minus 0.6? Because it is really opposite. So let's redo that. Y by x squared, x is equal to minus 0.6 this time. And that's equal to minus 6 times x, evaluated at x equal to minus 0.6. And since it is minus, it is clear that it will be plus 3.6, which is greater than 0. That implies this is a local minimum. That could be, of course, a situation where you have it exactly coming out to be 0. In that case, you cannot really conclude anything about whether it is a maxima or a minima, and usually you say that's a saddle point. Right? If by any chance, in this case we don't have that situation, if second derivative is exactly equal to 0, that's called a saddle point. It is neither a maxima nor a minima. And an example could be, so an example of that is if I were to do y is equal to x cubed, and its plot will look like the following. Its first derivative will be 0 at x equal to 0. Second derivative will also be equal to 0 at that point, but it is neither a maxima nor a minimum. On one side it is stable, the other side it is unstable. So in this case, second derivative of y with respect to x squared is actually equal to 0. So we would like to use this concept in what we are doing, and we will call this stability analysis. So let's go back to our idea of potential energy curve and how can we learn this from that, or learn something about the stability of the function. Yes, Christian.
Aren't we supposed to take those derivatives and put a negative in front of them as well?
No. Did I say something? No, right? I took the second derivative. This was already having a negative sign.
But when taking the derivative of work to get force, aren't we supposed to put a negative in front of it?
About the force, yeah, I have not talked about the force. This is mathematics, right?
Okay.
This is not physics. When it comes to physics, you will see that yes, there is a negative sign in front of it. So this will be slightly different, yeah. But let's not. I'll do that in a few minutes. Okay. So this is just mathematics. Any function, if you have a function here, how do you interpret whether it's a maxima or a minima? I'll do this in physics, where instead of talking about an arbitrary function y, I will talk about the potential energy. There you're right that there will be a negative sign showing up. Okay, so let me proceed and hopefully that will get clear. Okay. So this is, we'll call this stability analysis. And true only when there is a potential energy available to it. Whenever the force that is making the particle move is actually a conservative force. In that case, we can use these concepts. Right? Remember our idea here that force in one dimension is equal to negative derivative of the potential energy with respect to x. Right? That's what you were, Blake, I think you were trying to say that, are we supposed to take a negative sign in front of that? Yes, if we're talking about force, then there is a negative sign in front of it. And we'll see how it matters. Okay, so that's your force. And if you're interested in potential energy itself, du or change in potential energy, when you integrate this, is equal to negative x initial to x final times f times dx. No need to specify the path because if the first relation is true, that means it's a conservative force, and in that case, it is independent of the path. So if I had a curve for potential energy, and we would like to know what is, so that's your u, that's my x. Let me take a specific example. Let me say u of x is equal to ax squared minus bx4. This is very similar to what appears in your homework, but the example I'm going to do here, I'm going to say a is equal to plus 16 joules per meter square. Notice this is a positive quantity. In your homework, this is negative. That's very different in the sense the plot will change completely. In fact, it will flip opposite to whatever we are going to do here. So be careful. You can use the analysis, but it is different in your homework. Let's say B is equal to, let's say 3, right? Plus 3 joules per meter 4. Let's say 9, right? So that yeah, let's give it 9. 9.0, so 2 digits. So that's 9.0 joules per meter 4. So if I were to write this without the units in there, what I have is 16x squared minus 9x raised to 4. That's fine. Plot without the units showing up. How does this look like here? For small values of x, x squared is very dominant over x raised to 4. I can make x small enough that this will always be 2 dominant over that. In that case, I can drop that. So around x equal to 0, it is like a quadratic function. So it looks like this. A quadratic polynomial is like that. When it comes to large x, x raised to 4 is significantly larger than x squared. Think of a million, right? X raised to a million. This will be 10 raised to 24 then, and this is only 10 raised to 12, significantly smaller. So you don't have to worry about this. And then you notice that, oh, that's negative for large x. So this is somewhere here, this goes negative. And same thing on the left-hand side. In fact, it is symmetric between x and negative x because it's square and it's an even function. So it seems like the function will be like this. And in fact, if you were to plot this, it will look like this. In your homework, this has to be flipped exactly opposite. Since A and B are negative, it's a mirror image of the plot with respect to the x-axis. The idea is, of course, to find the maxima and minima at these 3 points, and to also determine whether those points are stable points or not, and we will define what stable points are. So first, let's begin by saying what are these. So when does this u itself go to 0? U goes to 0 at 3 points, right? So when is u is equal to 0, that is given by 16 x squared minus 9x4 going to 0. Let me pull that out. So I have x squared and 16 minus 9x squared is equal to 0, which means that x is equal to 0. So there are two values. X could be plus or minus, but x is equal to 0. And x could also be 4 over 3, right? So x is equal to plus or minus 4 over 3. That point is about 1.3 there, minus 1.3, and that's 0. Those are the three values. And since we have units for x here, so this is 4 by 3 meters. So 1.3 meters. That's good. We would like to actually know at what point is a force 0. In your homework, I write the question as what is the potential energy at the points when the force acting on the system is 0. So what is the force? Force is negative of the derivative. And what does that mean? So take any point here. So for example, at this point, right, what is the slope? Slope is a positive. Think of a tangent, that's positive, but force itself has to be negative. Slope is positive, but force will be negative because I multiply by that. Negative of a positive will be negative, so that means it is towards the origin. And it's always with respect to the origin. When we say positive or negative quantity, it is with respect to the origin. That means the force will be in this direction, which is clear. As I said, there was an analogy that whenever you have a potential energy curve, imagine that this is really a valley, and if I were to put a ball here, it will roll towards the origin here, and that's your idea of force. So what is minus du by dx algebraically? This is 32x minus 9 into 436 x cubed. So if I were to ask when is force equal to 0, so at what point is the force equal to 0, I would set 32x minus 36 x cubed is equal to 0. So that's x equal to 0 is a solution. And the other solutions are plus or minus 32 by 36, right? Plus or minus square root. Oh, did I do this? Yeah, I did do this. So that's a square root of 32 over 36 meters. That's equal to 0, and that's 0.94. So that's 0 and plus or minus 0.94 meters. Those are the points where the force is equal to 0, and force equal to 0, remember, means that slope of the curve has to be 0. That's this point here. That's this point, and at this point. So this here is 0.94. So that's plus 0.94 meters. That's minus 0.94 meters. And x is equal to 0 is also a point where slope is 0. Okay, so that's but now we would like to understand what are these points like if I were to keep a small ball here and disturb it very infinitely tiny by a really small amount. It is clear that it will slide off, right? Either to the left or to the right, it will slide off. It will be almost impossible to have it exactly standing there unless you get very perfect, but then a very tiny disturbance will move it off. And that will mean this is an unstable point. So just visually, this is an unstable point. And mathematically, if we go back to our maximum minimum principle, that's second derivative of the energy, right? not the force. If you're talking in terms of the force, then I have to do negative of that. But if I think in terms of U itself, the second derivative of energy should be negative at that point, and we'll verify that. At this point, if I were to take the second derivative of U, it should come out positive because this is a stable point, right? That's a stable point. Just conceptually thinking, if I were to disturb this a little bit, it'll push it back here. If I were to put, I think of it as a real value, right? I've been trying to repeat this again and again that whenever you have a potential energy curve, whatever the physics of that potential energy is, go and make it look like a value. I mean, imagine that that's a real value and you're talking about gravity. And this is also unstable. So how do we see this? So let me erase this part so that I can do this again, right? So I think we can. So let me write that down here. U is equal to 0 is x equal to 0 and plus or minus 4/3 meters. Right? That's just some information there, and so that I can erase this one. We already found the first derivative to be this. Oh, did I do this correct, by the way? Help. I messed up, right? When I did this negative sign here, I forgot to multiply this negative, right? So up here, so du by dx is not really 32x. Let me do this again, sorry. So u was 9x squared minus 16x squared minus 9x raised to 4, and du by dx was 32x squared, 32x minus 9 into 4, 36x cubed. Correct? And that's du by dx. So when I do the force, I have to multiply by a negative sign. I forgot to do that. So if you allow me to change the sign here, do this. So this is equal to minus sign here. So let me circle that. I changed that. I circle this, I make this a positive, right? Whatever I wrote, I'm changing that. So all the changed quantities are with the circle. From this point, when I set it to 0, it actually doesn't matter, right? When I set something to 0, I can always put that with a negative sign. But just to keep that, let me have this. This I changed to positive. And the result doesn't change, right? This still stays the same. Everything is okay. Okay. So that's my first derivative. Force requires a negative sign. One of you guys pointed that out earlier, insisted on that. Yes, force has a negative of the derivative. But now when we are doing stability analysis, I don't take that force and take the derivative. I start from here and I do second derivative of u. So second derivative of u with respect to x squared, or with respect to x, second derivative with respect to x. And now that is 32 minus 36 into 3, that's 108. So that's 108 x squared. Okay, so that's second derivative, but we are interested in finding whenever the force is 0, I want to check if it is stable or not. So at each of these 3 points, I want to see what is the value of this. Is it positive or negative? So let me evaluate that. So first let me start with 0. So second derivative of u with respect to x evaluated at x equal to 0. So I set x equal to 0 here, that's just 32. And that's greater than 0. if it is greater than 0, immediately I conclude that this is minima. Like remember that as a function, it is minima, but now I don't say it is a minima, I say it is stable. Like whenever the function or the energy is a local minima, that means as far as dynamics goes, this will be a stable point, or it is in stable equilibrium at that point. The particle is at stable equilibrium. Let's do this for the other point. Let me say du by dx squared evaluated at x equal to, what was the other point? That's 0.94, or let me go back to, let me say this is plus 0.94 meters, and that comes out to be equal to 32 minus, since it's an x squared, I will have to square the 0.94, which is nothing but 32 over 36 when I square it, whether it's plus or minus, it doesn't matter. So that's minus 108 times 32 over 36. 36 goes 3 times, so that's minus 64. So that's equal to minus 64. Which is less than 0. Which is less than 0. That implies that this is an unstable point, or the particle is in unstable equilibrium at that point. Again, if the plot is there, it's very intuitive here. If you were to imagine this to be a valley or an actual surface on your table where you have such a shape and you were supposed to keep a ball there, a slight disturbance will make it go off from that point, and that's what is understood as an unstable equilibrium. What if this was a negative point here on the left? Since this is an x squared here, right, it doesn't change at all. So this could be the negative point also, and that comes out to be exactly the same analysis, because again, this will be 32 over 36, and that will come out to be minus 64, and we get this to be an unstable equilibrium point. So that's a quick example there. I'll point out a few things about the next example in your homework. I won't really do it. So another example is if you have the energy to be beta over, this is again from your homework, minus alpha over r. Let me flip the homework problem. Let me say beta is greater than 0 and alpha is greater than 0. In your homework, this is negative. Both are negative. So it's exactly opposite to what you have, what I'm doing here. So again, if you were to plot this function, always imagine r to be small or large, right? That gives you a good idea of what this function is going to do. When r is really small, since r is in the denominator, small r means the very large value of u. And when r is small, this is going to dominate this term, right? 1 over, think of a micrometer, 10 raised to minus 6 over 10 raised to minus 6 square. That will be much larger, right? So this is significantly dominant for large r. And it is a negative value. So somewhere down there, this is dominant, but that's a negative value. At the same time, it is 0, right? It's approaching 0 for a large r, where r goes very large. Oh, did I say that correct? Yeah. When r is, I think I was saying it wrong. When r is very large, 1 over r is very small, and 1 over r square is much more smaller. So I don't have to worry about this. This is what dominates between the two, but it is relatively small, so it approaches 0, but it approaches 0 from the negative side because of the negative value, and that is alpha greater than 0. In your homework problem, this flips. What about when R is really small, that extremely small, then if R is a small, 1 over R will be very large, but then 1 over R square will be much more larger. So this is going to dominate there, and it is positive value. If beta is greater than 0, it's a positive, very, very large value, and it will go like this. In fact, it will approach to infinity when R equal to 0. 1 over 0 is an infinity. But if you have to start from a negative and reach a positive, so somewhere it has to turn. So this function actually looks like this. So that's your potential energy, and this plays a very important role in chemistry. This is how atoms interact, if you want. When they are very far away, the potential energy goes to -0. When they're very close, it tries to become an infinity. So somewhere in between, there is a sweet point where the atoms like to. So in a crystal, they are stable because the atoms try to be here, where the energy is minimized. In nature, always the energy is minimized. So if you want to find this value, you will take the derivative. So you will find du by dr this time. And if you want to get the force, you will do, you will get multiply it by a negative sign. You will then do the second derivative of u. And if you have got this plot correctly, then this should come out to be having a positive value, right? Because it is going to be stable there. So you have to show that this is actually greater than 0 so that it is stable. In your homework, this whole plot will be flipped because alpha and beta will be negative, and in that case, this will come out to be a maxima point. And I'll not proceed further in the class here with this example, but hopefully that gives you enough information. In the last about 12 minutes, I want to generalize this to 3 dimensions. It's just an idea. I won't test you on these concepts, but it's very useful to see how this generalizes to 3 dimensions. Question?
I was about to say that the camera needs to be moved, but then you moved it.
Okay, thank you. Thank you very much. Yes. Okay, so very quickly, a simple crash course, 2-minute crash course on partial derivative. If you've not seen this, let's think of let's have energy in mind. So energy is a function of position, and in general, you could depend on x, y, and z. Correct? As of now, we were working with a single variable that was x coordinate. In general, this could depend on all values. In that case, a change in u will be given by, I can change it with x, y, or z. This will be, notice the notation has changed. This is not really looking like a d. This is a curved d, just called a partial derivative with respect to u of x. And then you say this is dx. But that I could make a change with respect to y also. dy plus partial derivative of u with respect to z dz. What does this partial derivative mean? A simple example. Consider a very simple example. So let's say u is equal to some random function 3x squared y z plus 4 x y square. That's it. Right. What is partial derivative of u with respect to x? When I am doing the partial derivative with x, treat y and z as constants. You already know how to take derivatives. As far as you treat y and z as constant when you're taking the derivative with x, that's all you need to know. So here this will be 6xyz. And this is having x raised to 1, so that's plus 4y squared. Notice the idea there. Partial derivative of u with respect to y, that will be equal to 3x squared z plus 4y squared. Hopefully you're seeing the pattern. And partial derivative of u with respect to z would be, there's only one place here, this is constant, so that goes away, so that's 3x squared y. So that's all there is to it. And these are derivatives in the x direction, y direction, and z direction. That's how you want to interpret this. Now, I have force by definition is equal to, let me actually think of the following way. Du, change in or differential statement of energy is minus F dotted with dr. But that's a dot product between the force and an infinitesimal displacement. That's the same as minus x component dot product, right? So that's a minus x component of dx minus the y component of dy and minus the z component of dz. That's my definition of force right here, or the connection between force and potential energy is this. This is coming from the idea of partial derivative. And this is, in physics, we have seen that differential change in energy is given in terms of force this way. If I were to compare these two, so I'm using the idea of partial derivative with the idea of force. If I were to put this together, I learned that my x component of force is minus derivative with respect to x. The only thing I have to change is almost the same as whatever we did here, except that I now have to do partial derivative with respect to x instead of total derivative in one dimension. The y component is negative of the same energy with respect to y. And f of z is the partial derivative with respect to z. So pretty much everything goes through in each of the direction, except that I have to keep in mind that I'm doing partial derivatives instead of a total derivative. So the force then can be written as, this is x, y, z component, right? So I'll say this is minus I hat partial derivative of u with respect to x minus j hat partial derivative of u with respect to y and minus k hat partial derivative of u with respect to z. Same idea, it's just that there are three pieces to that, the vector generalization. Right? In fact, we should construct a vector for a derivative. Now, there are three derivatives in x, y, and z. So the idea now is going to be, this will be written as negative. I'm going to start a symbol. So this is called a gradient operator of u. So how does that show up? So notice that maybe I can write it here and it will show up clearly. Minus I hat d by dx minus j hat d by dy minus k hat. Does that fit in? Yes. D by dz, all of it operating on u, right? That's what the symbol is. That is an operator which has three components: derivative, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z operating on the potential energy. That's that symbol. So this is called a gradient operator, which is now a derivative in 3 dimensions, and that has the symbol. And this you will see in vector calculus if you have not already taken the course. This is the first thing you will see when you're doing vector calculus. So this is the generalization of derivative that you have done for a single variable in vectors, right? So this is the derivative operator, and this will be called the gradient operator. So in real world, potential energy is dependent on a vector quantity x, y, z, and the force is the negative gradient of potential energy. I won't do too many, or I won't do any examples. This is just for your information, a bare introduction to the 3-dimensional world here, and I won't test you either in exams with it. But I want to do, in the last 2 minutes, I want to do one more concept, which is again relatively simple. And okay, so this is the idea of power. Power will be denoted by the letter P. This will be broadly energy over time. That's all you need for that. But there is a nice thing when you actually are working with potential energy. That is a small little thing you can do with this expression, and that's the following. We saw that negative change in potential energy as a differential statement is F dotted with the infinitesimal displacement. That's change in potential energy, and that's a force and the displacement. We want to do power is when you divide the energy with time, but since it's a potential energy, now we can do calculus with this, and instead of dividing it by finite time, I divide it by a tiny infinitesimally small time. And I can do this. I can divide by delta t and take the limit and associate this dt with that dr. In that case, if I were to define, since power is energy and include the negative sign to this, so power for a conservative force will be minus du by dt, and dr by dt is just velocity, right? So we have this nice feature that power comes out to be the dot product of the force and velocity, only for potential energy. In general, power is energy over time, but if you have a potential energy associated with the force that we are talking about, then power can be interpreted as a dot product between force and velocity. Again, you will see this here and there, especially the idea of power, not really immediately in any of the chapters, but later in electricity and magnetism, in circuit diagrams especially, we will talk about power. But I'll stop at this point with this, and next time we will start with the new concept called momentum, and that will be pretty much stop. With that, we'll stop introducing new ideas, and then we will repeat it with rotation. That's all. Thank you.
Have a good night.
You too, Blake. Thank you.
Thank you as well.
I have a quick question about the homework, if that's okay.
Yes, sure.
So just in the first problem, it asks about whether or not like forces are repulsive or attractive. I was just wondering, like, what does that mean when we say a force is repulsive or attractive?
Oh, sure. I can explain that. So we have I think this is how it looks like, if I remember the homework, correct? That's your X, that's your
Right.
U, right?
Yeah.
What it means is that force, remember, is equal to minus du by dx. Okay, so let's consider this to be the point we are talking about. That's this point, right? So let's say x1. Okay, x1 is this point. At that point, draw a tangent, right? That's a tangent. Look for the slope. That's a positive slope, agreed?
Right.
So that means the derivative of u is positive. So at x1, so f of x1 is equal to negative of a positive slope. Agreed?
Yes.
Which gives me a negative number, right? Negative number means I think of a force, so think of a vector quantity here. Positive force will be away from the origin. Negative force will be towards the origin.
Okay.
Does that help?
So then we just describe a repulsive force as something that pushes away from the origin, attractive force going towards the origin.
That's exactly correct. Yes.
All right, thank you very much. That helps a lot.
Okay, good. Yeah. Any other question? Joey? Okay. Let me close then. Bye, Joey.